Hello, this is Todd Frazee, and this is ADVM 12, Unit 11, Positioning Tolerance Expanded Principles by Todd Frazee. Introduction. As functional requirements become more complex, so does the need for precise and clearly defined tolerancing strategies. You will learn how to apply functional gauging techniques to verify hole positions specified at maximum material condition, or MMC, and how to construct and interpret composite position feature control frames. We will also examine how the use of identical datum feature references across multiple position specifications can impact the design intent and inspection. Additional topics include specifying separate pattern requirements for feature groups, tolerancing inline holes, and using position controls to manage symmetry and coaxial features. This lesson will equip you to apply these expanded principles to complex part designs with confidence and clarity. Okay, objectives. By the end of this lesson, you'll be able to explain functional gauging concepts for checking hole position tolerances specified at MMC. Specify and explain composite position feature controls frames, and explain in the effect of using identical datum feature references in multiple position tolerance specifications, and specify separate pattern requirements for groups of features not acting as a single pattern, and specify position tolerances for inline holes, and specify position tolerance to control symmetry, and specify position to control coaxial features. Okay, composite position tolerances. Now, a composite frame, I want to note that you notice on the left the position symbol is in a rectangular box and there's only one symbol, and it applies to everything to the right of it. There is a way to have those separate in separate frames, and the way you interpret it is slightly different. Okay, but the feature control frame on a composite frame contains one position tolerance symbol and two or more segments. So each line would be called a segment. The first segment locates the pattern tolerance. So that would be the tolerance of all of the features, and all of them have to meet that tolerance. So it's typically looser than the next one, which is the lower segment. Feature relating tolerance is the tolerance of the features themselves individually. Okay, datum features references same order as the first segment with the same modifiers on this type. So in this case, the tolerance referred to A, B, and C is a diameter of 38 thousandths with maximum material condition, but in reference to datum A, you have 16 thousandths. Okay, pattern looking tolerances, tolerance zone framework. Okay, established by the first segment of the composite position tolerance. Same effect as the single segment position tolerance specification. So if it just has one line, you interpret that first line the same way as one that just has one line. Okay, and basic dimensions give the true position within the framework. And it's constrained in translation and rotation relative to the reference datums. Now, feature relating tolerance zone framework is established by the second segment of the composite position tolerance. It affects the location of all the features relative to one another. Basic dimensions within the framework, and same as pattern locating TZF in regard to true position between features. Okay, so the whole pattern, the entire whole pattern in this case, has to be within 35 thousandths position, and then from hole to hole, they have to be within 15. Only constrained in rotation relative to the reference datum. So you notice it's only datum A. So the pattern has to be within skew, is what I would call it. But since in this example only datum A is referenced, relative to each other, they've got a little bit of room that it can move, and they have it exaggerated in the graphic here in the lower graphic. Okay, composite position tolerance segment anatomy. Requirements in each segment met by the same set of holes. Feature-related zone tolerances within or overlapping pattern locating tolerance zones. And locations and orientations of true position axes as at basic dimensions relative one another within the feature-related TZF framework. Feature-related tolerance zones centered on true position. Okay, here's datum feature reference effects on feature relating TZF. Okay, feature relating tolerance zone may not be need a datum feature reference. So in the first example, there's no repeating datum reference. All repeated datum feature references in the lower segment must exactly match those of the first segment. And pattern locating tolerance datum feature references repeated to achieve desired constraints on rotational degrees of freedom. Okay, no repeated datum feature references. Must meet the tolerance requirements of both segments. The feature relating TZF not constrained in translation or rotation. An example of repeated datum feature reference must meet the tolerance requirements of both segments, and the feature relating TZF constrained in rotation relative to primary datum. So in this case, it's only in reference to datum A in this example. And it's free to translate relative to the datum reference frame. So in this case, it would only constrain really the holes perpendicular to A. Okay, repeated primary and secondary datum reference features. So if there's two datums referenced, must meet the tolerance requirements of both segments. The feature relating TZF constrained in rotation relative to primary and secondary datum. So looks like you can have a shift, but you're not going to have feature rotation on one axis there. It's free to translate relative to the datum reference frame. Okay, verification of feature relating tolerances. Okay, measurements record for computer processing or manual evaluation process. Feature to feature data organized into a table. And paper gauging process using the axis method is acceptable, but it will not accept parts that violate allowable position tolerances. So there's some error in that method. And it may result in rejection of marginally good parts if you use that version. I don't see paper gauging used very often. It's very time consuming, but it is a good way to learn how the position tolerance works. Okay, so here's a feature related position variation from that prior graphic. You got holes 1 through 4. We have our measured deviations and difference in hole diameters. Okay, so the measurement data is used to determine the position variation of feature relative TZF. Okay, and here's determining acceptance using the feature relating hole-to-hole relative positions. So we chart it out. We have our maximum material condition zones, and acceptance is determined for feature-related position variation. Multiple and single segment feature control frames. Here's some examples. Position tolerance symbol for each segment. and different meaning than composite position tolerance. So you see how there's a symbol for each segment? What this does is it allows degrees of freedom in one axis and not the other. So in the example, you got your whole pattern, the entire whole pattern it's got its locating zone, and it needs to satisfy, all the holes need to satisfy this first segment of a diameter of 20 thousandths to datums A, B, and C. But they give you a little more freedom in one axis because there's a tighter tolerance between A and B, which just puts it really right to left, the way this is drawn. Yeah, so it's held tighter vertically, and you have a little bit more freedom vertically than you do have right to left. So in this example, you got to hold the vertical position in that axis to 12 thousandths, but in the horizontal axis to datum C, it has more freedom. And for those that have taken my machine shop class, we cover an example of a frame just like this in ADVM 67. Okay, functional gauging of position tolerances. Verify produced parts meet tolerance requirements using the surface method. And simple and complex gauges. Complex parts and tolerances impact the gauge complexity. And it's not required to verify tolerances. Metrology and mathematical processes. Consider variation of simulation process and verification process. Okay, so here's an example of gauging tolerances specified at maximum material condition. On the top we have a part. It has its position and it has maximum material condition on the holes 1, 2, 3, and 4. We've built a functional gauge, and the gauge they've drawn in a different orientation than the top view, but our datum B has a fence, if you call it, that the parts mounts up to for datum B and datum C, and it sits flat on datum A. Then we have these pins that come through that, if they all fit and meet the side of the fixture, then they should be within tolerance. Okay, so the simulated reference datum is the fences and the flat plane, and locate virtual condition gauge pins relative to the datum feature frame. So this is where you have to calculate that virtual condition of the hole. And the part must be properly contact the datum feature simulators with gauge pins in the holes. Okay, if it doesn't, then they're out of position. And the hole size is checked separately. And the gauge only verifies the position tolerance has not been exceeded. So it's not actually giving you a measurement. So if you have a fail on a hard gauge like this, you typically are going to go back and check it through another method. Okay, gauging when a primary datum is referenced at maximum material boundary, so that affects things. Okay, when no form tolerance is applied to the primary datum feature of size at MMB is this example. The datum feature simulator is fixed at maximum material condition size of the datum feature, and the feature fits the gauge snugly at MMC, free float if it departs from MMC. Okay, so gauging when a datum is at reference at RMB, the datum simulator establishes the unrelated AME, or by required contact with the feature. The unrelated AME, because the primary datum feature is not related to the higher precedence datum. Okay, the effects of the secondary and tertiary datums references at MMB. The simulator size determined by applicable MMB of the datum features. So at MMB, it's same as applicable virtual condition. The exceptions are geometric tolerance of 0 at MMC applied, and the datum feature reference shows the required value. And the primary MMB is equal to MMC if no virtual condition created by a form tolerance. Simulation of secondary and tertiary datum references at MMB. So it's possible to use a single gauge due to datum features related to one another if the MMB modifier on the datum feature references and pins used to check the hole locations always size to the virtual condition if position tolerance includes the MMC modifier. Gauging a composite position tolerance. So pattern locating gauges simulate all reference datum features. Constrains translation and rotation of pattern of the TZF relative to the reference datum features. Pins at hole true positions relative to the datums at the size of the virtual condition. Feature relating gauge simulates only reference datum features in the applicable segment. And it constrains the rotation of feature related TZF relative to the reference datum features. And pins at true position within the TZF are sized at the virtual condition calculation of the hole. Okay, simultaneous patterns for position tolerance. Applicable to single segment and pattern locating tolerance occur when position tolerance reference the same datum features in the same order with the same material boundary modifiers. The TZFs create a simultaneous tolerance specification becomes one zone. The exception is taken by noting separate requirement or SEP REQT on a single segment or pattern locating tolerance segment. Okay, separate patterns for position tolerance. Applicable to feature relating tolerance, second or third segments of the composite tolerance. Each creates the TZF acts separately, and exception taken by noting simultaneous requirement or SIM REQT on the feature related to the tolerance segments. Okay, so here's an example of simultaneous required referenced on a flat datum feature. It acts as one pattern because both have position tolerance with identical datum feature references. Only one functional gauge is needed to verify the hole locations. Okay, so here we've got two sets of holes. They're called out to the same exact datums, and they're called out to the same exact tolerance, and they have the same modifiers. So you can use one fixture that picks up on your datums A, B, and C that fence the part in, and then you have your holes made at the virtual condition that the pins stick out and the part has to slide on there without it binding on any of the surfaces. And there can't be a gap against the fences.